So in this video, we're going to talk about ways to increase the parallelism beyond the pipelining we've already talked about. We've talked about pipelining, which allows you to execute multiple instructions at a time. So what are ways? So let's if multiple instructions, we did 5 at a time with our pipeline. If 5 is good, is 20 better. So how can we make this better? One way is to make a deeper pipeline, and there are examples in the ARM instruction set has a deeper pipeline. Some of them have like a pipeline of 14 stages. So is that good? Today in this video, we're going to talk about, could you execute multiple instructions at a time by issuing 2 at a time, having more hardware. So we're going to replicate pipeline stages, so actually like doubling up some hardware in order to do 2 at a time. And so you could start multiple instructions every clock cycle, and since what we're looking for is to do more than 1 at a time, we're going to use instructions per cycle rather than cycles per instruction. So we could, if we could issue 4 at a time, perhaps we could get to a CPI of 0.25, which would be a instructions per cycle of 4. But this would be the upper limit of what we could get, and we probably won't get it because of dependencies and hazards, just like we've already talked about. So we're going to look at 2 kinds. Static multiple issue is where we replicate some pipeline stages and issue 2 at a time, and they go through the pipeline just like the single. So they go through together, 2 at a time, go through all the stages. They go in that order, so it's static. We can decide which 2, we can put them into the pipeline out of order, but once they're in the pipeline, they're going to come out the same order they went in. Dynamic can actually, things can change inside the pipeline with dynamic multiple issues. Each cycle, a different one can go forward. And there are advanced techniques that you can look up if you're interested. Some graph techniques and algorithms to resolve hazards. So here's some of the techniques we can use. We can reorder instructions, which the static you can reorder, but once it's in the pipeline, they come out the same they went in. You can include, so with the dynamic, you can actually add other instructions to fix up the mistake. You can buffer results. We'll see example of that, buffering results until they're needed. So put something through, and in our example, we buffer the results so they come out in the same order they went in, but there's, during it, they kind of switched around a little. While in the pipeline, they switched orders. And flushing buffers on incorrect speculation, we saw that with branching, and even if that wasn't dynamic. Scheduling, we still saw what it's like to, you speculate on the result of the branch and then flush if you were wrong. So first we're going to look at static multiple issue. The simpler, you group, if you say that you can do 2, you group them into issue packets of 2 instructions, and then they go through at the same time through the data path. And if you see something called very long instruction word, maybe in your research you'll see that, in the platform you research for your paper, maybe you'll see that, but that's actually just 2 instructions packaged together. So you can reorder them into the issue packets. Obviously, you can't have a dependency within the packet. You might be able to have dependencies between packets. That's kind of an interesting thought. If you had to forward, would you know which part of the pipeline to forward to, and so on. But you can't have dependencies within the packets. So you might have to add a lot of NOPs, and we'll see in our example. So NOP is NOP, that's no operation. So it's just a blank. Here's the idea. Issue 2 at a time, and the one we're going to look at here that, there is, a MIPS, we'll look at a MIPS data path where you can issue one that uses the ALU or a branch, and you can issue one with a load store at a time. So this instruction in this slot has to be an R type or a branch. This one has to be a load or a store. Here's the data path. So you can see we can issue 2. One, so there's 2 sign extend, just in case, well, this sign extend is going to be needed for the load store. This ALU will calculate an address and go to data memory. And then this one will either do the sign extend for the branch, or it'll do the R type. So there's 2 separate paths here. But you can't put 2 R types at a time, because this one isn't taking input from the register, or it isn't taking 2 inputs from a register, it's just taking one. So again, you can't have a hazard in the packet, so you can't put these 2 together, because this load depends on the result of that add. So you're still going to have load use hazards with latency, but now we've added we have 2 instructions stalled. So we reorder things. So here's an example where we have a loop. We're looping through an array. So we're loading a value into T0, adding something to it, storing it, and then decrementing our pointer. So it looks like we're going backwards, downward through a loop, down to 0. So how could we schedule this? So we have to schedule an ALU and a load. And this load, so we're going to schedule this first. We can't put this add in. We can't put the store word because it depends on the add. We don't want to decrement the pointer yet because that's store word. So all we can do in the first stage is that load word. And then the next one we can put, we need to schedule one cycle between these 2 because of the dependency. So we'll stick this add in because it doesn't depend on that. And then, but actually, now I'm thinking, does this even work? Because won't that one be off? Can you even do that? I've used these slides for a while, but look, I mean, does that even work? Because now I've changed S1 before I store something into it. I guess I have to just start S1 bigger than or just add a 4 here so it's correct. Anyway, so now I have to schedule the add. Now I can do the add U. And then I can schedule, since I can do a branch and a load, I finally have one where I can schedule 2 at a time. So I didn't really help things that much here. So I've gone from 5 to 4. In this case, loop unrolling can help you do more parallel processing. So that's where you unroll the loop and kind of use more registers rather than do each loop with the same register. So we'll see what we're talking about here. That loop unrolled. So this is 4 times through this loop. And actually I'm going to start off with SI decremented by 16 because we know there's 4 instructions. So obviously I have to make sure these values are correct since I've already decremented by 16. Started out 16 higher than I thought. But here I'm loading into 4 different registers. So then as soon as I have this one ready, I can add into 4 different registers. And then I can store the 4 different registers. So that's 4 times through the loop. So what would have been 14 with only 1 instruction going at a time has now 8. So I've increased the code size and the number of registers, but I have also increased the instructions per cycle. So the other example that we talked about was called dynamic multiple issue, where we put something in, almost like we queue up instructions and decide which ones to issue. And during each cycle, so each part of the pipeline, we can decide which one moves on. So rather than the compiler, so in the earlier one, the compiler kind of ahead of time decides the scheduling, here the CPU is deciding the scheduling. So the CPU decides to execute instructions out of order, but they're committed in the same order, and we'll see that example. So we look at this, queue them up, and we decide, oh look, this one maybe I could start while we wait to do this one. So it's just done not at compile time, but at runtime. So here's our example. We're going to fetch all of our instructions and kind of queue them up here. Decide which one, so these things can all be happening in parallel. So I could actually, in this example, send 4 at a time if I had the right instructions. Then they might sit, ready to go here until we send them this commit unit that's back in order. And then if I need something from this result, I can, a little arrowhead got lost, but there's supposed to be a little arrowhead there, got lost. So if I'm doing a load and I need something from that, I can send it back to here, or if I have a load and it needed to go to this, an R type, it could go back there. So these hold operations that are pending, and results are held here, and then committed in order. So here's our example. And in our example, we're going to assume we can fetch and decode 2 instructions at a time. So it's going to take 2 cycles, 1 to fetch, 1, and then in cycle 1 you would fetch, second cycle you would decode and send to a reservation station. So I'm just going to try to draw out with some understanding how this works. So in cycle 1 we're going to fetch load word and add you. And in cycle 2, the load word and add you are going to be decoded and then sent to reservation station. So we'll send the load word here and the add you here. And then we'll also fetch the sub and the SLT. In cycle 3, we're going to send the load word into its unit. So what's going to be in here is going to be the regular execute, mem, and write back. And I'm actually going to assume here, I haven't found good examples of MIPS that use this, but I have seen I did see others where there can be different units and different number of cycles to get through these functional units. So let's assume that in this, the cycles are execute and write back. So it takes 2 cycles to get through this and 3 to get through that. It's just a theoretical thought, I don't know of MIPS that can do that, but let's just pretend that's how this works. Anyway, so in cycle 3, we've started the load word. The add u isn't going to start yet because it depends on that load word. The sub and the SLT, we can also send the sub, and we can send the SLT. Maybe we'll send it to the same one. Okay. Let's do some pink. Cycle 4. So in cycle 4, we have load word is going to go to the mem. We're going to send the sub through, sub we'll send through. We'll do the execute. This one still has to wait. It has to wait for after mem. Cycle 5. We'll have load word go to write back. Now we can send our add u into the X. Execute. Sub will send a write back. And we'll start our SLT. So now the sub and the load word are done in cycle 6. To get a good color. How about pink? It's not that different from 4. Anyway, so now this is done. That's done. We're going to put add u through write back. We're going to put SLT through write back. Now we're going to, next, all of them are done, so we can then send, back to the commit unit in the same order. But in 6 cycles, we executed all of this.